Welcome to Groups, Homomorphism. In this segment, we'll do Proposition 20. Proposition 20 needs some explanation, just to make sure that we're on the same page with the notation. Proposition 20 states that every group G is isomorphic to some subgroup of A of G. It's a very powerful result. It essentially shows that, any group that you can think of will be sitting inside the permutation group A of G. Okay, let's review some notation. Let f from S to S be a one-to-one function. Let A of S be the set of all such functions, one-to-one functions, and let star be the usual composition operation, the little circle between functions, that is f of g of x is f of g of x, right? The usual composition operation. Then A of S is a group, and it is a non-abelian group because we know that f of g is not the same as g of f. Okay, so specifically, if S is equal to 1 to n, then a one-to-one onto function f from S to S is called a permutation. For example, if f is a function from 1 to 5 to itself, then this is a permutation. 1 gets mapped to 3, and this is how we write it. 2 gets mapped to 1, 3 gets mapped to 4, 4 gets mapped to 2, and 5 gets mapped to 5 itself. So we denote A of S in this case as Sn, and call it the symmetric group of order n factorial. The size of this group is n factorial, right? The set of all permutations from n to n. And when we say permutation group, we usually mean A of S or any of its subgroups. S could be anything, and in general, we can take S equals 1 to n and talk about the symmetric group. So we're ready to do Proposition 20 with a clear understanding of the notation A of G. And that's not a typo here. This is every subgroup G is isomorphic to some subgroup of A of G, the permutation group on G itself. So A of G is the set of all one-to-one functions, right, from G to G. And define FA F subscript A like this, X, F subscript A of X equals AX. The operation star is there, but it's usually suppressed. We don't put it. We would have to put it too many times if we put star everywhere. All right, so let's define F subscript A from G to G as F subscript A of X equals A of X. So we'll show that F is one-to-one. F subscript A is one-to-one, so F subscript A of X is equal to F subscript B of X, implies AX equals B of X, and that implies by the right cancellation law, A is equal to B. So therefore F is one-to-one, and just a note that the opposite implication also indicates that FA is genuinely a function. In case you were wondering, is F subscript A really a function? Well, the opposite implication establishes that, so it is a well-defined. A equals B implies AX equals BX, implies FA equals FB. All right, so let's put that down. Okay. Then we will prove that F is onto. And here we have to think a little bit about onto. So if a member of G is X, and we have to find something that will map to X, right? Something in G itself that will map to X. And the natural candidate here, with a little bit of trial and error, would be A inverse X. So f of A inverse X, G, A is in G, and G is a group, right? So, so this would be f A inverse X, f subscript A inverse X, let's be precise here, is equal to A times A inverse X. And by associative property of groups, you get this, and that's just E of X, and that's equal to X. So here we had to do a little bit of trial and error to take an element X of G and then come up with its pre-image. All right, and I think we should specify here that A is also in G so that its inverse does exist. Now, observe that FA dot FB of X, right, is equal to FA FB of X. That's the meaning of composition here. So this is F subscript A, B of X. So this is A, B of X. Right, I'm applying what the function FA means. And this I can write by associative property of groups. This is ABX, and this is FABX. All right, so FA dot FB is equal to FAB. Let T, let's define the set T, be the set of all FA such that A is in G, right? And now this is a subgroup of A of G, which consists of all one-to-one functions from G to itself, and define the operation as FA star FB equals FAB. Right, and that is just, I suppose we can just put dot over there, FA dot FB, right? So, and define FA inverse from G to G in this manner. So the inverse exists of every function. And we will show that T is a subgroup of A of G. Now FA dot FB inverse is FA. I'm sorry, the inverse should be up here. And the next round, so let's start again. F subscript A dot F subscript B inverse is F subscript A dot F subscript B inverse in this manner here. So that is F of AB inverse. And since AB inverse is in G, this belongs to A of G. G is a group, AB inverse belongs to G. So we may conclude that F subscript AB inverse is in A of G. All right? So that takes care of this claim. T is a subgroup of A, G. And now we will define an isomorphism. We have to prove it's an isomorphism from G to this subgroup of A of G in this manner. And we will prove that it is an isomorphism. And that will give us what we want. That is, G is a subgroup, isomorphic to a subgroup of A of G. All right, to show that it's an isomorphism, we'll show that it is one-to-one and onto, and homomorphism, right? So we'll start out by showing that phi is a homomorphism. Right? Phi of AB is equal to F subscript AB, and that's F subscript A dot F subscript B, and that is phi of A, phi of B. All right? So that takes care of homomorphism. Next, we will show that phi is one-to-one. Phi of A equals phi of B implies F of A equals F of B. That implies AX is equal to BX, which is A is equal to B. That takes care of one-to-one, and onto is immediate, because for every F of A, there exists A such that phi of A equals F of A. This, in this case, onto is immediate. Therefore, phi is an isomorphism, and we can conclude that G is isomorphic to T, and that's a subgroup of A of G. And this completes the proof. So that was quite a longer proof. We began by defining this function F of A in this manner. F of A, F subscript A of X is equal to A of X, and we showed that it is a bijection. It's one-to-one and onto. Then we defined F A, subscript A dot F subscript B in this manner. We defined the set T, and then showed it's a subset of A of G, and we showed that it is in fact a subgroup of A of G. Finally, we defined the isomorphism from G to T in this manner. Phi of A equals F subscript A, and showed that it is an isomorphism. And thus we concluded that G is isomorphic to T, which is a subgroup of A of G. This concludes the proof of proposition 20. I'll see you in the next segment. Bye.